Claudio Bonanno will speak about topological susceptibility at high temperature.
Okay. Good evening. Today I'm going to discuss some new results about the computation of the topological susceptibility in full QCD at high temperatures using the staggered spectral projectors approach. This work has been done in collaboration with all of the people that are listed here, very crowded collaboration. And I want also to thank the organizers for this opportunity. So first of all, let me start from the physical motivations behind this work. Of course, this topic has been already discussed extensively. So in the context of the QCD axion as a dark matter candidate, we are interested in computing the axion effective potential at high temperatures, so at 30 times of the universe evolution, because we need this input to compute useful quantities, such as the relic abundance of the axion today, which are also essential inputs, of course, for present and future experimental searches for this particle. And so, since the parameters of this effective potential are related to topological observables of QCD, of course, we are interested in computing these observables at high temperature for axion cosmology. And in particular, I'm interested in the topological susceptibility, which is the leading order term, because it is related to the mass, the effective mass of the axion. And if one wants to compute chi from lattice QCD, there are several non-trivial computational problems that have to be faced. And in particular, in this talk, I'm focusing on this one, which is related to essentially the presence of the adoption, if you want, of non-chiral fermions in the action. So the starting point, as we all know, is that in the QCD path integral, field configurations are weighted with the determinant of the Dirac operator, which can be, of course, written as a product of the eigenmodes of this operator. And the index theorem in the continuum relates the topological charge of the background field gauge field configuration to the presence of zero modes in the spectrum of the Dirac operator, number of left modes minus the number of right modes. So on typical configurations, this means that if a configuration has a non-zero charge, the lowest eigenvalues that appear on the spectrum of the Dirac operator in the background of that configuration are proportional to the quark mass. So this means that in the presence of light quarks, this implies a suppression of these configurations in the path integral. And also note that this eventually leads to the vanishing of the topological susceptibility when we take the chiral limit. On the lattice, however, if we adopt non-chiral fermions in the action, for instance, staggered fermions, which are the ones that we have adopted in this work, we don't have exact zero modes because, of course, they would be chiral otherwise. So this means that this suppression is not as efficient as in the continuum because we have the so-called would-be zero modes. So essentially, we have a shift in the lowest modes, and this shift is expected to vanish in the continuum limit. So why this is a problem? Well, this is a problem because this bad suppression implies that large cutoff effects appear if we consider the continuum scaling of the topological susceptibility, especially at high temperature where we expect it to be suppressed as a power of the temperature. This is, for example, a plot taken from this work for 170 MeV, so above the zero critical transition. And as you can see, there are large systematics affecting the continuum extrapolation of chi towards the continuum limit. And in the end, we end up with essentially 100% error on the extrapolation. So several strategies have been proposed in the literature to overcome this problem. For instance, the solution proposed by the WB collaboration in this work is to essentially reweight configurations in the path integral essentially replacing the actual staggered Dirac operator eigenmodes that we compute on the lattice with their corresponding continuum Lewis eigenvalues, which are proportional, as I said, to the quark mass. But another possible solution, which doesn't require any ad hoc assumption, could be instead to change our definition of the topological charge, which is usually defined, as you all know, in terms of the gluon fields on the gauge link variables, using a sort of index theorem on the lattice, and to define a sort of fermionic definition of Q. Because the naive idea behind this approach is that maybe if we use the same bed operator to weight configurations and also to count eigenmodes to compute Q, this may introduce smaller lattice artifacts. And this idea is actually supported by the results that have been obtained at zero temperature in this work here, using Wilson fermions, different mass Wilson fermions, where if we compare the computation of chi using this approach of spectral projectors, which I'm going to discuss in the next slide, and we compare it to the standard computation using the Bloch definition and the gradient flow, we observe much smaller cutoff effects for chi. So the main goal of this work is to essentially adopt a similar strategy, but using staggered fermions, and in particular adopting the same definition that has been done, has been given in this work, where I contributed, in order to study chi at high temperature in full QCD simulations where staggered fermions have been also employed in the action. So this essentially is our definition of the topological charge. Essentially, what we do is to introduce in the continuum definition, which is just the trace of gamma 5, our spectral projector. The idea is just that since we do not have zero modes, we just sum all the modes up to a certain cutoff mass m. And the role of that spectral projector is exactly that. So to cut off the mass at a certain value of the eigenmodes. I will discuss better the role of this mass in later slides. So in order to compute the projectors, we essentially diagonalize the staggered operator, or better, I times the slash, which is Hermitian, so the eigenvalues are real. We compute eigenvectors, and then we build our projectors multiplying the eigenvectors. But that's not the end of the story, because we also have to keep into account the mode degeneration related to taste degeneration. So we have to divide by the number of tastes. And this is our essentially bare definition. We can also show that this bare definition only gets a multiplicative renormalization, which can be related to the renormalization constant of the scalar and other two scalar fermionic densities. And this quantity here, this ratio here, can be expressed as well in terms of traces of the spectral projectors and of gamma 5. The capital gamma 5 is just the staggered version of the Dirac, usual Dirac gamma 5. So in the end, we obtain a fully renormalized expression for Q, only expressed in terms of traces of the spectral projectors. So as for the choice of this cutoff mass, which for now is just a free parameter, of course, we expect this choice to be relevant in the continuum limit, because in that limit, only zero modes must contribute to the topological charge. But of course, we expect lattice artifacts to depend on the choice of this value. So in particular, we need to ensure that we keep the normalized value of this cutoff mass constant as we scale towards the continuum limit, in order to guarantee that we have order is square lattice artifacts at leading order. And in particular, this is the renormalization of the mass in our setup. So in order to avoid the direct computation of this renormalization constant for each lattice spacing, our strategy is just to observe that for staggered fermions, the quark mass renormalizes exactly as the cutoff mass. So since we know a line of constant physics in our setup, it is just sufficient to keep the ratio between m to any of the quark mass that you have in your theory, your lattice theory, constant as you scale towards a continuum limit, in order to ensure that mr, which is the normalized value of the cutoff, is kept constant in physical units. Okay, so now one can wonder if there is an optimal choice for this cutoff mass. In particular, one would like to choose it in order to reduce the value of this coefficient here, C, which parameterizes the cutoff effects that you have in your definition compared to the gluonic case. So in order to try to answer to this question, we essentially computed the chirality, which is this quantity here, R, through the eigenvectors that we have computed in our simulations, because we know that in the continuum limit, of course, R must be either 1 for 0 modes or 0 for the other modes. So in principle, the idea would be to choose the cutoff M in order to include all relevant would be 0 modes in your spectral sums and exclude the non-chiral modes. But as you can see from this scatter plot of the chirality versus the magnitude of the modes, it is very hard to clearly distinguish between 0 modes, so chiral modes, and non-chiral modes. As you can see, the maximum value of the chirality that we observe is about 0.6 in this at this lattice spacing about 0.057 Fermis at 0 temperature. So this is an example at 0 temperature. So what we did is essentially to find, let's say, an optimal interval where we try to include all the modes that look chiral enough on this scatter plot. And essentially, we compute the continuum limit of chi in for several different values of the cutoff in this interval in order to check that everything is working as we expect. Because of course, we cannot just choose just one value. So our setup is 2+1 rooted south-staggered fermions at physical points. So we have physical quark masses and physical pion mass, and physical, of course, quark mass ratio between strange and light quarks. And we follow a line of constant physics to keep these quantities constant. So this is the continuum scaling that we get for the gluonic standard definition, and also for two different values of the cutoff mass M inside the interval that I showed you, where I choose the strange quark mass in order to fix my cutoff mass. And as you can see, in the optimal interval that I have determined from the chirality, we observe a reduction of the magnitude of the lattice artifacts for chi. And also we observe very good agreement between the continuum extrapolations obtained for different values of M, and also with previous determination from gluonic definition, from chiral perturbation theory, L leading order, and also with very much larger error from the gluonic computation using our configurations. So everything seems to work fine. So we performed a more systematic study. So we, as I already said, we extrapolated the continuum limit of chi for several different values of the cutoff mass inside the optimal interval that I showed you. And so, as you can see, we observed that all extrapolations are quite in good agreement between each other, because we at most observe 1 sigma fluctuation. And we also observe a reduction of lattice artifacts compared to the gluonic definition, because I plot here the ratio between the artifacts for the spectral projectors and for the gluonic definition. And however, we carefully take this error bar as our final determination for the 0 temperature case. But in any case, everything seems to work fine. So we adopted the same strategy also at finite temperature, where, of course, it is interesting to adopt this definition. So the 0 temperature case, if you want, is just a check that everything is working as we expect. So again, we look at the chirality also at finite temperature in order to determine our optimal range for the cutoff mass. This is an example for a temperature of 430 MeV on a lattice with lattice spacing 0.0286 Fermis, so quite fine. So here, as you can see, there is a, if you want a more clear separation compared to the zero temperature plot, because we have, let's say, we have a cluster here with high chirality of the order of 0.8, and a cluster here with small chirality, which is smaller smaller than 0.05 almost. But however, we also have a sort of limbo in between with quite some modes which are not clearly falling into one, of course, class or the other. So again, the strategy that we have devised is to choose an interval and to try to select different values of the cutoff inside that interval to check what happens. And of course, in this case, we arrive up to m over ms of the order of 5, because we just, let's say, avoid including modes in this cluster here in our spectral sums. So the let's setup, of course, is the same of the zero temperature case, and also in this case, we observe that it is possible, choosing the cutoff mass in that interval, to reduce lattice artifacts compared to the glowing definition. As you can see, the red points here are the points obtained through the standard glowing definition, while these are the spectral projector determinations. And we obtain a good agreement between each other, and also there is also agreement, at least between 1.5 sigma, with the determinations from the WB collaboration work. And also in this case, we have performed a more systematic study of the value of chi as a function of m. And also in this case, we see that essentially we observe agreement between different extrapolations at different values of m, and also we observe that it is we observe that we are able to reduce lattice artifacts, at least for not so large values of m, at least like up to m over ms about 2, we have a factor of 2 or larger of reduction in lattice artifacts. So this is our final error bar for the determination at this temperature, which is 430 MeV, which also consider all the little fluctuations that we observe when we change the value of m. So, so we repeated this approach for several values of the temperature above the transition, and we arrive up to about 600 MeV. And so we studied the dependence of chi on the temperature. So from the Dialton gas approximation, also called DIGA, we expect chi to drop as a power law above the zero critical transition, with an exponent that, if we take the fourth root of chi, is expected to be around 2. And as you can see from our B-log plot, we observe a very good agreement with the decaying parallel, and these are the exponents that we obtain, which of course within the errors are compatible with the DIGA result, although they are a little bit smaller. And if we compare our results with the results from the WB collaboration obtained in this work, we observe that, as they also show, there is a compatibility with the exponent predicted by the DIGA, but there is a mild tension between our data and the data from the WB collaboration. So essentially, our prefactor seems to be So the prefactor in front of this power law with our spectral data seems to be larger, about a factor of 3. So we still do not have a clear understanding of why there is this discrepancy, but it may be related to the different ways that the different strategies that we have adopted to reduce the lattice artifacts affecting chi. So this is certainly something that is worth investigating more. So come to my conclusion. So my take-home messages are that so we have observed that spectral projectors provide a theoretically well-posed method to define the topological susceptibility on the lattice, and they are very useful to reduce the lattice artifacts affecting the standard Wang definition, because they can be tuned essentially by choosing wisely the cutoff mass n. So I showed you also that systematics related to the choice of the cutoff mass m are well under control, so we are able to safely extrapolate towards the continuum limits using spectral projectors. And if we study the temperature behavior of chi, it is possible to find a good agreement with Dagger prediction within the errors. So we find a decaying power law with the temperature with an exponent which is compatible with 2. So of course, it would be interesting to include higher temperatures on our study, where we expect spectral projectors to be even better. But if we want to reach temperature of the order above 700 MeVs on the typical lattices that we can afford, of course, we need lattice spacing of the order of 0.01 Fermis, where we know that we have to face a severe topological slowing down using standard RHMC algorithms. So a promising candidate for a viable solution to, let's say, reduce the effects of the topological slowing down could be the parallel tempering on boundary conditions algorithm that has been proposed some years ago by Azenbush, and that it was adapted in this work where I also contributed to a pure Young series. So in principle, it can be extended also to the case of full QCD. So it is a solution that it is worth being explored in the near future. So I'm done, and thank you for your attention.
Okay, thanks you, Claudia. And there are some questions.
Yeah, thank you very much for the talk. It was very interesting. How do you calculate the eigenvalues? I assume you use some Arnoldi or Lanczos method, and then, if so, how much of the eigenvalues you calculate to get to your optimal mass?
Mm-hmm. So to compute the eigenvalues and the eigenvectors, we use the RPAC method. So the Arnoldi algorithm, if you want. For this example, we computed up to 300 eigenvalues. So if you want the first 300 lower eigenvalues. In this range here, the mean number of eigenvalues of eigenvalues that we include in our spectral sum varies from the order of 10 here for the left edge of this interval, from up here, which is about the mean number of modes is about 30. So this is the mean number of modes that we include in our spectral sums. We observe that it scales almost linearly with the cutoff, which is, I mean, what we expect actually.
Okay, I just another question here. Then I see there is a remote one.
Thank you.
So when you first showed that the fermionic definition of the topological charge and then went on to the definition using the spectral projectors. So given for staggered fermion, there is no exact zero mode. So somehow this, I mean, that's why usually staggered fermion for any spectral properties or anything is it not so straightforward. So does that have anything to do or that gets somehow improved in by doing this spectral projection? I mean, like overlap, it doesn't have exact zero mode. So
well, yes, essentially the idea is that if you essentially if you cut the sum up to a certain cutoff, you are essentially cutting away all ultraviolet noise, which is larger than the value of the cutoff. So that is the main idea of the spectral projectors. If you want, it is like adding a Heaviside function in your definition of Q. So you are just leaving away all the modes higher than M, which if M is chosen as I explained, are expected to be just the contribution of non-chiral modes, which must vanish in the continuum loop. I hope I answered your question.
okay, then please, Leonardo.
Hi, everybody. If you read the original paper where the spectral projector were introduced, you see that they were introduced, yes, also to compute the topological susceptibility, but essentially to compute the chiral condensate. Did you try to look at the chiral condensate on your configuration with the spectral projector as a function of the temperature?
Thank you for your question. I was actually discussing exactly this point with Claudio earlier this morning, and we did not try, but we of course plan to take a look at this data. So in principle, of course, it should be possible to adopt the same strategy of the original paper to compute the chiral condensate. And as I also said before, while answering to another question, I also took a look at the dependence of the mean number of eigenmodes that are included in the spectral sum as a function of the cutoff, and it seems almost a linear relation as we expect from the relation that relates the number of modes and the cutoff mass through the chiral condensate. So this is surely something that is worth checking also at finite temperature to see what happens. So thank you for the question.
Okay, there is maybe time for one short question, if there is still something.
Just your last slide, you said about using a new simulation algorithm in future, but does that mean you're just using the HMC now, or?
Yes.
And also BMW, they now work?
Yeah, well, we are working on it to include fermions. Yeah.
Okay, so let's thank the speaker again, and